what we're going to do is we're going to, I guess, use this velocity graph to verify the information that was in the position graph to show the displacements and such. So I assume that's what you're wanting me to do here. So to do that, I want to remind you that what's plotted on the vertical axis is velocity, and what's plotted on the horizontal axis is the time. Now, as we discussed yesterday, the thing I would encourage you to always do when given a new graph is to identify what information you can get from looking at the slope and looking at the area. So you should always consider the potential value of the slope and the area. So the slope, we take whatever is on the horizontal axis, the vertical axis, and divide it by whatever's on the horizontal axis. So that would be meters per second divided by seconds. That's the meaning of the slope. If that looks like something that is familiar to you, then the slope has meaning. If it doesn't look like something that's familiar to you, then the slope doesn't have any meaning to you. Don't get me wrong, it could have meaning and you just don't know what it is. But if you don't recognize that unit, the slope might not have meaning to you. Do the same thing for the area, which takes the product of the vertical axis and the horizontal axis. So that's meters per second times seconds. And when I do that, I get meters because the seconds cancel out. Now, does this have meaning to you? If meters has meaning to you, then the area likely has a meaning. So because the area appears to be something that might be in meters, so that could be a length, a position, a distance, or a displacement, we should test the areas to see if the areas can do something for us. So when we talk about area, we are physically talking about an actual physical area. Length times width, something like that. And so I'm going to identify that this is a rectangle. And it appears that in this rectangle, I'm going to have negative 2.5 meters per second times 12. Questions about that? 30, I'm pretty sure. 2 times 12 is 24, half of 12 is 6, plus 24 is 30. That seems like 30. But there's a negative sign there, so negative 30. Now, this suggests that the object moved away from the origin in the negative direction 30 meters. It did so in the first 12 seconds. That's kind of what I see here. Started at the origin, moved to the 30 meter mark in what appears to be 12 seconds. But I have more areas to test. So there's this area. And here's where students may make mistakes in interpreting what this is. I have a length of 5 meters per second and a width of, is that 6? Yeah, 6 seconds, which means this area is also 30 meters. Well, together that means there's a total displacement of 0. So in the next 6 seconds, I must make it back to the origin. Because I'm already 30 meters behind the origin, so I must be making it back to the origin, and indeed I do. I move over 6 seconds, and I'm back at the origin. And the last area, this one, 18 to 30 is 12 seconds. And that's going to be this width, but the height, oops, don't want the eraser, but the height here, that's 2.5. So that appears to be another 30 in the positive direction, 30 meters. So I'm expecting that I'll travel 30 meters, yep, that's 30, and did so in another 12 seconds. Now, looking at the position graph, my total displacement, 30 meters. I am 30 meters from where I started. When I add these three numbers together, I should get 30. And I do. Total distance traveled, when I look over here, I went 0 to 30, then 30 to 0, that's 60, and then 0 to 30, that's another 30, so that's 90 total. So over here, add the absolute values, 30 plus 30 plus 30 gives me 90. Is that satisfactory? Excellent. You're welcome. I did not fully understand what you wanted me to do. Y'all good with that? Now, if you can do that, you should have had no trouble with the second page. Because this is exactly what the second page is asking you to do. These graphs are all velocity versus time graphs. And an important distinction is a velocity versus time graph has to be more interpreted to figure out how the object moved. There's more to do. And there's things that a velocity versus time graph cannot tell you, like where the object started. It can't give you that information. I want to remind you that because of the software I use, it's probably best that you mark where 0 is. You'll be happier. And if you've done this one, then great, you're just going to follow along. If you haven't done this one, then I would actively follow along. Like maybe jot this in your notes so you have something to work from. But note that I already posted it, so you could just look on Canvas and see that it's there. And you guys are finding the things I'm posting on Canvas okay, right? They're showing up somewhere appropriate? All right. So you have to be giving a starting point. And although I have the answer here, let's go ahead and get rid of it so that we can kind of work through this. I gave you a starting point. I said, assume that the object starts from the origin. That means that no matter what, for every one of these graphs, you're going to start by putting a dot at the origin. That's where the object begins. Time 0. And just like before, when you were making the velocity graph from the position graph, here we're making a position graph from a velocity graph, but they still are capturing the same event. So this event took 10 seconds. So this graph should go to 10. And just like before with the position graph, if you have what appears to be some kind of special thing that seems to happen, like an abrupt change, you may wish to mark that moment on your velocity graph. So I see an abrupt change at 2 and an abrupt change at 6. Do you guys see those? So I'm going to mark 2 and I'm going to mark 6. Places where an abrupt change took place. Now, the idea here is in order for me to understand a position graph, I need to understand how the object moved. Now, there's a couple of ways you could approach this. For you guys, I'm really going to focus on one, but there are some pretty smart cookies in here, so there are other ways to do this. One of the things is to remember that this set of graphs over here, the velocity graphs, are slopes, which means you could establish a grid on your position graph and just put in the slopes, like you're doing slope-intercept form with an algebra class. It's not how I'm going to do it. That's how you could do it. I'm going to do it different. I'm going to encourage you to use the areas that are clearly represented here and have it find the displacement in each interval. For example, there's no displacement in the first interval. 0 meters per second for 2 seconds means it traveled 0 meters in 2 seconds. That's easy to identify on the position graph. The object didn't move for the first 2 seconds, so at 2 seconds, it's still at the origin. But this other area, where the object was traveling at 2 meters per second, that's this portion, and did so for 2 seconds. That suggests a displacement of 4 meters. So the object, starting at the origin, moved in the positive direction 4 meters. Now, I'm going to take a guess here and suggest that I'll put 4 up there. I don't think it's going to move further away than that. It's clear the next area is going to be negative, but you might have to look ahead to see whether you can, put the 4 there. You have to try and use as much of the graph as possible. And now that I know what I'm graphing over here, I'm going to write position, because the graph is never complete unless it's labeled. Time. Make sure they have units, so I don't have to write it next to my numbers, and kind of flesh this out so I have nice, even increments in both directions. So I'm going to continue now. I'm going to put a dot here to indicate that at 6 seconds, the object is now 4 meters away from the origin. So I've lined up this dot with the 4. Questions so far? Yep.
I thought that it would be like 4 seconds because from 2 to 6 we have before. Why is it 2?
Because Mr. Shelton can't add. Thank you for pointing that out. And thank you for pointing it out now, not like in 10 minutes. That's good. So I apparently wasn't looking closely enough, being distracted, I guess. And this is not 2 seconds. 2 to 6 is 4 seconds, making this 8 meters, making this 8 meters. So I'll make that 4. Thank you. That's going to be in the video. So you should mark on your calendars. It is August 19th. Mr. Shelton was wrong. My family does that to me. They put it on my calendar and then put it on auto repeat so I see it every year. Anytime I make a mistake in front of them, it's on my calendar. We have a shared calendar in our house. Love my family. But sometimes they can just rot, if you know what I mean. All right. Next area. We good to go? Everybody saw my mistake? So here we go. Next area. Not big. Looks like it's got a width of 4 seconds this time. Let's get it right. And a length of -1 meter per second. This suggests an area of -4 meters. Now here's where people make mistakes. That doesn't mean I go to the -4 meter mark. That means I start here and go back 4 meters. This is a displacement. So I have to change the position from where I am to where I'm going. So starting there, I'm going to go backwards 4 meters. Now, here's where we talk about how you get full credit for doing this. You have to connect these dots. Straight lines connect dots when the velocity is constant. All of these velocities were constant. So these should be straight lines. And when I say straight lines, I mean you have access to a ruler. They should be ruled lines. Anytime you want to make sure that a person who is grading your test understands that a line is purposefully straight, means it should be ruled. So tomorrow when you're doing this for your test, have a ruler out or a straight edge out to ensure ruled lines as part of what you are doing. Questions? All right. So what I'd like to do now is first recognize that we're done. That's a position graph. We've taken the information and placed it on a position graph. To ensure that you guys kind of know what you're doing, I'd like you to do this next one, if you haven't. And if you have done the next one, then do the next one. Pick one of these to do. Prove that you can do this, because where we're going after this is going to be harder. And if you're not an expert at these, you'll be unable to do what we're doing next. Mark 0. Make sure you do that. If you don't mark 0, you will be unhappy. So I'm going through and marking 0 so that we know where 0 is on these, but you should do the same. But pick one of these to make sure you do. And I'd start with this one if you haven't, and perform this one. Be an expert. Because trust me, where we're going in a few minutes, it's not going to be as easy. So if this were my homework and I was faced with this question, the first thing I would do is recognize what I have to do, and that is to create a position graph. I always find it nice to just kind of remind myself what that means. This is going to be where the object is. But I don't know where it is. I do know how it's moving. And it looks like it starts at 5 meters per second, has an abrupt change here at 4 seconds. Then it travels at -1 meter per second until 9 seconds, and then -3 meters per second for a second. So I'm going to put the 10 here, and I'm going to mark 9 because an abrupt change occurred at 9, and I'm going to mark 4 because an abrupt change occurred at 4. The problem told me I can begin at the origin, so I'm going to mark the origin. All right, so I think I'm ready to go. It looks like it moves forwards first and then backwards. I want to keep that in mind because I need an idea of my scale on the position axis. I need to choose a scale that will accommodate how far the object moves. So to figure out how far it moves, I'm going to look at the areas on my velocity graph. The area of a velocity graph is displacement. So length 5 meters per second, width 4 seconds. This is positive 20 meters. We do this area too. I do all the areas together. I'm going to end that area right there for this section. And this is -1 times 5, so -5 meters. Then this last section, -3 times 1, so -3 meters. So it appears the object went forwards 20 meters, backwards 5, and then backwards 3. So I think I will set the maximum range here all the way up to 20, because I don't go any further than that. And I'm going to subdivide it. So I have 5s, 5, 10, 15. This will maximize my use of the graph. In the first 4 seconds, the object went from the origin to the 20 meter mark because it had a 20 meter displacement. In the next 5 seconds, the object moved backwards 5 meters. So, and then the next 1 second, it moved backwards 3 meters. So I just kind of marked the dots about where they go. Now I'm going to connect these dots using an appropriate way of connecting them. All of these were constant, which means all of my slopes have to be straight, because my slope on the position graph is the velocity. I like that. That worked out okay. Just a quick look around the room suggested that we might need a little practice, so we're going to do the next one too. But I think this time, if you're not catching on, you really should ask me when I walk around. So the next one, I'm going to make it big so it can be easily seen around the room. And let's have you guys have a go at it. And when we come back together, I'm going to ask you guys questions about what I should do next and have you guys step me through this. Let's go ahead and get started with this and see what we can do. Raise your hand if you can tell me where I'm going to start on my position graph. Yes, sir?
0, 0.
So I'm going to mark 0. And go ahead and label it. That a good thing? I like labeling them. So position, time. All right, so which axis can I do like right now without having to do much thought? You're a great help. I'm going to try and hit some other people up, right? How about Luca? What do I do next? I know yours is right.
So you calculate the area of like the 0 to 1 second.
All right, I could go with that. So calculate this area. What do I get?
-2.
-2 meters. Now, I don't have any units put on my other graph yet, so before I go any further, I really do like to label the points where things change and how big the time axis is going to be. So, although I know Lucas is right, I've got to do this because otherwise I don't feel like I can do it right, so sorry. So there, I've labeled all the points where something important happened. So, with Lucas' information, it looks like I'm going backwards first. And I'm going to be someplace below the position axis. That's not a problem. Remember, the origin is just a relative place. So we can move in front of it and we can move behind it. That's no big deal. The real problem is I don't know how far my axis needs to be. I mean, I could put -2 here, but I think my graph might be out of sorts if I do that. So let's go and look at, I see one big area coming up. So how big is this area? Somebody let me know. Yes, sir?
6 meters.
6 meters. So I'm going backwards 2, forward 6. That seems to me like, all right, so I can make this 4. And now I've got a decent scale for everything. Follow why I did that? I need to have an idea of how big my scale is going to be. So now it looks like I go backwards 2. From here I go forwards 6. That's going to take me to the 4 mark. Now, what happens next? Yes, ma'am?
It like stays the same.
Yeah. Why does it stay the same?
Because the velocity is at 0, which means they're changing position.
Exactly. Exactly. And then in this last second, what's going to happen here? Really? Nobody? Yes, sir.
You're going to drop 1 unit.
All right, I'm going to go backwards 1 because of this area. All right, so that's it. I just gotta connect all them dots together. Straight lines, of course. And we're done. These are really just practice for the main event to get you accustomed to what you need to see. And that is that when you have a velocity graph, the areas tell you the displacements. It's really the important detail here, because this is the one we need to become able to deal with. This one is really more about what I want you to see. Look carefully at this one, please, and note how it is different. Unlike the prior examples, in this example, you'll notice that the object's velocity starts at 50 meters per second, and it's positive, so it's going away from us at 50 meters per second. That's fast, right? Half a football field every second. But after 2 seconds, it's going 30 meters per second. And that's a constant transition that's taking place here. After another 2 seconds, it's only going 10 meters per second. And again, a constant transition is taking place here. This object is moving. It's always moving in the positive direction. The velocity is always positive. But would you agree it's slowing down? In fact, what's its velocity right here at 5 seconds?
0.
It's not moving, it's stopped. Now, nothing is different from what I said earlier. What I mean by that is there is still an area here. And because there's still an area here, I can figure out what the displacement is. Now, this isn't a rectangle. It's a triangle. You're going to have to dive deep into geometry or second grade, right? 1/2 base times height. You remember how to deal with the triangle, or if you don't, shame on you. Your poor elementary teacher who spent all that time making you cut triangles and do stuff. The base appears to be 5 seconds. Remember, we have to bind our curve against the 0 mark. So 5 seconds there. So 1/2, 5 seconds. And the height seems to be 50 meters per second. You can do that. You guys are good at mathematics. I've checked most of your scores. 1/2 of 50 is 25. 5 times 25 is 125 meters, and it's positive. Seems to me that we can start doing this one. Nothing's different. I mean, there is obviously something different, but I can still hit that 5-second mark and 10-second mark. I can recognize that in the first 5 seconds, I move 125 meters from the origin. Put a dot there. I'm going to look at my last 5 seconds. And the area is from the curve to the horizontal axis. So this is going to be 1/2. The base is 5 seconds. And the height is negative 50. Negative 125. So the object comes back to us. We're going to have to stop here, but you should think about what we'd have to do to connect these together. I'm going to keep talking because I'm recording, but you should think about it. For example, this is the slope at time 0. It's a slope of positive 50. This is the slope at 0. It's 0. And this is the slope at 10 seconds. It's negative 50. How would you connect these together? It wouldn't be a straight line because it's always changing. So yeah, it's probably something parabolic like maybe. All right, we'll talk about this tomorrow, obviously.